Well, it's a real pleasure to have this chat with you, Raghu, about your work and your view of mathematics. But before we start, since we've known each other for a long time, I'd like to start with your early days in mathematics. Take you back to India. Where did you start liking mathematics? How was it in school and in undergraduate studies and graduate work?
Well, it's difficult to say when real interest in mathematics developed. I think from a young age, I was always interested in games, like chess. My mother taught me chess, I think, when I was 4 or 5 years old, and I always enjoyed playing chess. And so sort of planning multiple stages and sort of logical thinking and so on was sort of developed early on. So from that point on, mathematics, multiplication, arithmetic, and so on wasn't really a challenge in any sense. It was all somehow natural.
And you went to the neighborhood school, I presume, in India. Schooling is...
I grew up in a small town not too far from Madras, Chennai as it's called now. There was only one school in town. Everybody went there, so there was no choice.
Great.
And I was there, I think, for a few grades, and I skipped a couple of grades. And then once I started high school, it was steady. High school means there, from the middle school on, it's called high school.
Where did you go to the university as undergraduate?
Well, when I graduated from high school, in those days in India, they had 2 years of junior college. That's where I studied. I studied mathematics, physics, and chemistry as my 3 main subjects. So at that point, when I finished, I could go to graduate school, either in mathematics or physics or chemistry. And I didn't really want to do straight mathematics, but statistics was more interesting to me because I had heard a little bit about statistics from my high school math teacher. He told me it was a very important field to study. So that was interesting to me. And the other alternatives were physics and chemistry. So I tried to get admission into any one of these. Admissions are tough. There are, colleges have 10 seats or something, and the whole state has probably a dozen seats for admission to. This is a special honors program, which is what I was interested in. So whatever I thought I would get first, I would join. It turned out I got statistics first, so I joined statistics. If I had gotten physics first, I would have gone to physics. Anyway, it worked out well.
And there I remember you had some very lasting friendships with some of your classmates in graduate school, right?
There were graduate school and graduate school. Because I went to junior college, then I got my first real degree. That's already a different institution. So there's a 3-year honors program, which gives you a combined bachelor's and master's degree together. In statistics, we are a very small group of 13 students, And I think a dozen of them are still alive today. And we are still very close. We keep in touch. And whenever I go to India, and we get together for dinner and keep in touch with them. Then I went to Calcutta for a PhD degree. When I arrived in Calcutta, I wasn't that much interested in mathematics. I thought I was going to do a PhD in statistics. And I really was interested in doing applied statistics. So I started with something called statistical quality control. Somehow it struck me as something that was important. I don't know why.
The title is fancy enough.
The title was fancy enough. And so I started reading it and somehow didn't find it very interesting. I was bored stiff with it. And so I decided instead to spend my time playing cards and just wasting my time. So that lasted about 4 months into my first year of graduate school. And I met Parthasarathi, Rangarao and Varadhan. They were seriously interested in mathematics. And they told me I was wasting my time and I should just start doing mathematics instead. So I followed their advice and started on mathematics. And that was, we had a good group in the sense that we were all graduate students, and we made a program as to what we would study, and then we would take turn lecturing to each other because there are no courses offered in any mathematical topic whatsoever. So whatever we learned by ourselves. And so we met more or less every morning at 7:30, and one of us would give a lecture and the others would listen, and we would take turns, and that's how we learned the subject.
Without any faculty direction or?
No, not really. Some of them were more senior, a year or two ahead, so they knew more than what I did.
Right.
So they could at least say what I should read. But it was fun. We learned, and then we said, okay, let's put we learned basically aspects of functional analysis. That's what we learned. And then we said, okay, let's put this and apply it to any problem and try to solve a problem. So we took some problems in limit theorems and tried to use the techniques we learned in functional analysis to solve these problems, and we made progress.
So you chose your own problems without an advisor?
Yes.
Wow, that's quite different than the way we deal with graduate students.
Well, I suppose if I had gone in statistics, it would have been different. But in probability, which is what I ended up doing in mathematics, there wasn't really any real probabilist on faculty. They're all statisticians with some interest in probability. They gave a course on measure theory, for example,
Right.
and things like that. But I don't think I ever took a course from anybody in stochastic process. And so all these things we learned by ourselves.
Did you have access to journals, current journals, publications, to know really what's the state of research without having somebody?
In all the probability and statistics journals, we had an external library. Okay, and then we were members of the Indian Mathematical Society as student members, and the Indian Mathematical Society has a very good library.
Okay.
But it's located somewhere else in some other city. But if you write to them, they will mail you the journal.
Right.
And then you give the journal to your library. They'll make a photocopy. Those days, photocopy meant a photocopy. Somebody would take picture of each page with the camera, print it out, and print the copies in a huge bound volume for a 30-page paper.
Wow.
But still, it was available that way.
And current, up to date.
It's all correct. Maybe, they used to come by ship rather than airmail, so it would be a few months delay, but it was all there.
And you finished in what year, your degree?
I finished my PhD. I wrote my thesis in 1962, but it takes a year to process the thesis and get a degree. So I got my degree in 63.
And this is when you came to Courant?
Yeah, that's when I came to Courant.
So what made you apply to Courant Institute? You did not have the probabilist to advise you, so how did you choose the places to apply?
Varadhan, who was there when I first went to ISI in 59, he finished his degree at that time and went to the United States to do a postdoc. He spent a year at Princeton University, then he spent a year at Seattle, and then he spent a year at Courant Institute as a visiting member at that time. Then he came back to India and we overlapped for a year. That's when I finished my degree and got my PhD certification. And then we were thinking about places to go, and then he suggested that since I was interested in stochastic process and Markov process and connections with PDE and so on, he thought that Courant Institute would be a good place. So he suggested that I apply for visiting membership here. And it's an interesting story because he knew there are forms, application forms to fill.
Yes.
For a Courant to apply. So he wrote to Peter Lax, mentioning me and said that he sent the forms and so on for me to apply for visiting membership. That was, I think, sometime in October or November. Until January or February, there was no response from anybody. So since I wanted to go somewhere that in the fall, I went to my advisor. I had an advisor, C.R. Rao, who was a famous statistician. He was my formal advisor. I went and told him I want to go someplace. So he said, okay, you'll write to somebody. So he wrote to Wolfowitz at Cornell. And so I think within a week, a response came. And they offered me a position. In fact, I think it was even a tenure track position or something like that. So they sent a cable offering it. I felt since it was a cable, I should respond. So I responded, accepting it. And just the day after, a response came from Courant Institute, which was in fact an offer instead of an application.
That's funny.
It was signed by Moni Donsker, who was running the visiting membership program at the time. So I told my advisor, what should I do? He said, it's okay, it's just been a day. If you really want to go to Courant, you can write to Cornell how sorry you are. Then just go to Courant. Okay. That's how I ended up here.
It's indeed funny stories. Did you send the cable or write to them?
I wrote to them.
Was it the first time you left India?
It's the first time I left India, yes.
So that must have also been very different for you.
I came here, and then there was an organization, I think some international student organization or something like that. They said they would help me find a place to stay when I came. So they booked for me a hotel in Times Square.
Coming from just to Times Square is not necessarily a good idea, but okay.
In fact, it's called Times Square Hotel or something like that, some such name. And I think the room rent was $2.50 a night. I think I arrived on Sunday, so I stayed there Sunday night. And then Monday I came to Courant, and there was a Laser Bromberg was at that time sort of the administrative person here, although he was in the faculty, he dealt with the administrative things. His secretary was one Esther Fox. So I went to her and said, I'm here. So she said, okay, fill this up. And so, where are you staying? I said, I'm staying at Times Square. She was on board. And so I came to a hotel which still exists in some form, Albert Hotel. So I came on September 15th. I stayed there for 2 weeks till the end of September. Then I was going to get a room, some studio for myself to stay. Finding an apartment was not difficult at that time. I mean, I got a list of apartments. I went someplace. I saw somebody, and he showed me an apartment somewhere near West Village, near the 10th Street, near the river. It was a nice apartment, a studio, a third floor walk-up or something like that, and furnished. The rent was $125 a month.
Unbelievable. Yes.
And I told him that, look, I have no money on me because
you just came
from India. I had no money. I had brought couple of $100 or something. And I said, so I can't pay any advance at this moment, but I'll give you $20 to hold the room for me, and I will pay you on the first when I get paid the advance, and then I'll go move in. I said, that's fine. So that's what I did.
So let's say you came here and you came to the Courant Institute, and your first position was as a visiting member then, since Moni wrote to you about this. And how was the first year at Courant?
It was very good. I mean, we were, I was in 25 Waverly Place, and many of the lectures were in 4 Washington Place because the institute was divided between the two buildings at the time. In 4 Washington Place, they didn't have the entire building. They had a few floors. The other few floors was a hat factory.
Right.
So you go to the elevator and you look at somebody, you say, is he my colleague or is he working for the hat factory? If he was well dressed, he was for the hat factory. Otherwise, he was a mathematician. So anyway, it was a fun year because there was no teaching requirement, and there are some good seminars. There was a analysis seminar where somebody pointed out this distinguished gentleman with a beard. That was Louis. And so that I could interact with them, and I think I was influenced by Louis, Fritz, and Peter, and Jürgen. They were all influential at the time. And the visiting program at that time was huge because Sloan Foundation had given a huge grant for the visiting program. And I think every year we had about 30 or 40 visitors. It was nice. And the institute was really nice because that summer I went back to India to get married. And Vasu came here too. She just finished 1 year of college in India, so needed to be admitted to NYU. And so they admitted her. The tuition at that time was nothing like what it is today, but it was still $1,600 a year, which was quite a chunk out of my paycheck.
Yes.
So I asked them if they could do something. But as a visiting member those days was not an employee of the university, so I was not eligible for any tuition revision and so on. But they were nice. They gave her a fellowship, so she didn't have to pay any tuition. So that made it possible for me to stay here for 2 more years, and then I joined the faculty.
And when you came here, did you start to work with faculty at Courant, or did you work on your own in the beginning?
I worked closely with Moni. Although we didn't do any joint work at that time, you would discuss problems and so on. He would suggest some of the things that could be done, and I would try to do some of them. And then he had one student, Michael Schilder, who did some work on asymptotics of Brownian motion, which really is a problem in large deviations. And that got me interested in the subject, and that's how I got into the field.
Who were the faculty here that you came and saw when you moved?
I think although Varadhan wrote to Peter Lax, the person who responded to me was Moni Donsker. He was the one who sent the letter of appointment. I think Moni had just joined the year before. And the Courant Institute had received a grant from Sloan Foundation. A grant specifically to develop probability and statistics here. So they made some appointments. They made 2 appointments in statistics, Kumar Jagdev and Madan Puri. And in probability, they appointed Donsker. And the idea was to develop the area here. Sloan also gave a lot of money for postdocs at that time. We had enough money to support 20 or 30 postdocs each year. And so I saw Donsker at that time, and so we used to have a joint seminar with the Rockefeller University once a week. I think we would alternate between Courant and Rockefeller, back and forth.
At that time, who was at Rockefeller?
Mark Katz was there, but he had some visitors. Henry used to visit once in a while.
Henry was not here yet.
Henry was at MIT at that time. So he used to be on leave from MIT and visit Rockefeller. And then he moved permanently to Rockefeller at some time, and then from Rockefeller he moved here. And those were the only, there was one more Schreiber who was, I don't know exactly what he did in harmonic analysis. He was there. Those were the only people permanently. But there are a lot of visitors, and Mark Katz used to get many people to come and talk in the seminar. The seminars were very interesting always. I learned most of my statistical mechanics from being in that seminar. Jack Schwartz ran a seminar on Lie groups. Because I had some interest in Lie groups, I attended that.
Right.
But somehow it was more algebraic than analytical.
Mm-hmm.
I stopped for after a year, so it didn't really continue. I interacted a little bit with Kurt Szymanczyk. He was working on quantum field theory.
Right.
So I was trying to understand a little bit quantum field theory and so on. But I found it still rather difficult to really grasp and get moving.
Let's talk about large deviations, since this is one of the major areas in your early work, and you did some incredible work there. So you started the work after the student of Moni's work, and then did Moni join in? Because you have lots of work.
Not at that time. I mean, this was, 64 and 65, I worked on large deviations. And there was a joint seminar between Rockefeller University, I think at that time it was called Rockefeller Institute, and New York University Courant Institute, which I think in the fall it used to be there, in the spring it used to be here. And Mark Katz was running it there, and then we'd go there and come back. Once I was coming back with a group of us who went there in a taxi, and somebody mentioned something that somebody had done, that if you take a Brownian path and if you look at the ratio of the two fundamental solutions, one with free whole space and one Dirichlet bounded data for a domain, the ratio sometimes goes to 0, sometimes goes to 1. And for the ratio to go to 1, for all points in the domain need to be convex. The idea for that is that Dirichlet boundary condition means not exiting the domain, and Brownian motion in a very small time will go in a straight line. So what that means, between any 2 points, the straight line must be contained in the region, which gives you convexity. So that's the idea behind the proof. So when I heard it, I said, okay, what would happen if it was not a flat space? Okay, then if a diffusion went from point A to point B, then it should go along the geodesic.
Right.
Okay, turned out that was in fact a large deviation result, and I thought that should come from an asymptotic formula for small time for the fundamental solution, just like the heat equation, as u to the minus, whatever the exponent is, there should be a similar exponent. I asked Louis and the PDE people, they gave me various estimates, nothing was precisely that. So I was able to prove it, and then use that to prove the required large deviation principles and so on.
So you did this work, but still this does not illustrate to me when you started working with Moni and Dan Strock on this.
Well, this was still in 64 or 65 when I was still a visiting member. And I think essentially it was this work with PDE that sort of people liked at Courant and offered me a regular position. So I joined the faculty in 66. And just before that time, I had met Dan Strock at Rockefeller, and he was very much interested in what I had done, and we started talking, and then we thought that some of the properties that we used could be useful in characterizing diffusions. So we started looking at how best to describe a diffusion process, and we developed what we call martingale approach to diffusion problems. And this was something that Dan and I worked on essentially from 66 till about 72. And that was an important work because it sort of makes possible to define diffusion process at at least the definition is possible without using PDE. Then it's possible to define it in infinite dimensional spaces or other settings where PDE theory doesn't really exist.
Right.
Although PDE needs to come in if you want to prove certain properties of this or certain uniqueness properties and so on, there are various methods of proving it, and PDE is one of it. And what it does, it unifies various possible approaches.
So you did this work with
Dan
and
that was a whole series of related things, and this means you have new methods for proving limit theorems,
right.
and a similar thing with boundary and without boundary, and so there was a lot of related work that went on for a period of about 6 years.
Mm-hmm.
And then Dan left to go to Colorado, and I took a sabbatical, and I was in India because I had at that point 2 boys, and it was time to visit grandparents in India. So I spent a sabbatical year. Half of it I was in Sweden for half, and then in India for the other half. I came back in fall of '73. That's when I started working with Donsker on large deviations again.
Did you try to use this work on diffusion to do something in topology or geometry, because it was quite fashionable to use diffusion, the heat kernel, to get topological information? And did you try to go into that direction?
Not at all. I think I'll tell you exactly why. Because I didn't have a formal education in mathematics.
Mm-hmm.
My knowledge of topology and differential geometry and so on was absolutely zero. So I concentrated more on the probabilistic and the statistical aspects rather than on the, differential geometric or topological side.
So now you came back from India, and you started working with Moni again on large deviation. And how was it like to work with Moni? I know personally he was a very interesting man, but work-wise I never worked with him. So
he had a fantastic collection of problems.
Really?
And he had some ideas about how to do this problem and so on. And he would say, maybe it should be done this way, it should be done that way. So he was very good at coming up with nice, interesting problems.
With good intuition as well.
Very good intuition on how this would go.
Is there any particular problem you're fond of that you worked with Moni, or any particular result that you really like and from that work that stands out, or is it the whole collection?
Originally we started out with the idea that, if you look at heat equation with the potential,
Yes.
then the Feynman-Kautz formula, which tells you that the solution is some expectation of with respect to some Brownian motion.
Right.
So that expectation, which is the value of the solution at time t, you can see that it has a tendency to grow. And if you look at the eigenfunction expansion for it, it's clear the growth rate is exponential and has to do with the largest eigenvalue. The eigenvalue is negative, it decays. So you tell yourself that eigenvalue has a variational formula.
Right.
The variational formula is in terms of some Dirichlet form and so on. And then if you have an integral where the integrand is very large, then there is some kind of a Laplace asymptotic formula in function space, which should give you a variational formula too. That comes from variational formula through large deviations. Large deviations really means you have exponentially small probabilities.
Right.
If you have an exponentially large function that you are trying to integrate with respect to a measure which is exponentially small and some sets, there is a fight between the two, which is resolved by Laplace asymptotic formula, and that's a variational formula for the integral in some sense. So that's a variation formula over probability distributions.
Right.
Well, is there a connection between the two? Are the two variational formulas really the same? Are they different? Okay, that was the problem that Donsker asked.
Now I'm curious, did he ask it in this term? Because whenever I chat with you about probability, you are capable of putting the problem in terms of very elementary mathematics, in terms of Laplace's asymptotic formulas and how it relate to. So was Donsker like that as well? Or is this your explanation?
No, there was,
Because I'm always fascinated how you put the problem as much as by the solution of the problem. You always go back to the idea, the simple explanation.
Most problems are simple. I like simple problems.
I know, but not all people are capable of doing that, giving the simple explanation. What's the idea behind it? But let's continue with the problem.
So I was thinking about the problem for a while, what should the answer be, how to relate the two. And then I was visiting Duke University. They had invited me to give a colloquium. I think it was the fall of '73. So I was sitting there in their library, I had an hour before my talk. So I was thinking about the problem, and suddenly it occurred to me that the solution was very simple. I mean, the usual variational formula involves an L2 function.
Mm-hmm.
And if you square the L2 function, you have an L1 function. Right? The L1 function is a probability distribution, basically, with density with respect to Lebesgue measure. So any variation formula in L2, you can write it as a variation formula in L1. Of course, there is some ambiguity about square root, but the ground state eigenfunction is positive anyway, so there is no ambiguity of square root. So just redo the variation formula in L1 rather than in L2, and that has a very natural large deviation interpretation.
And you did this work before your talk at Duke.
I mean, once you have the idea, the actual proof is just, it goes.
Okay, that's beautiful. That's very nice. Very nice. So let's go back to homogenization.
Homogenization is taking limits of solutions of PDEs.
Right.
Now, if you have a second-order elliptic equation, the solution is the expectation with respect to some diffusion process. Mm-hmm. So you have a family of diffusion processes that depend on a parameter epsilon, and you want to show their limit is some other diffusion. And then its expectation will be solution of a different differential equation, and so that is the homogenized equation. So any homogenization problem of at least second-order elliptic operators can be reduced to a problem about limit theorems.
Mm-hmm, mm-hmm.
So you can handle it the way you would handle limit theorems. And of course, here now you are proving homogenization result without using PDE.
Right.
But then you're not getting any estimates at all.
Right. Now, I want to pause from the topic a little bit because you said something which is very interesting, and it came up with a conversation with Louis about proving things without using PDE, without using probabilistic argument versus PDE arguments. And this is what he was describing, some question he asked you about his work with Probabilistic. And your answer always started by, oh, this is obvious if you use probability theory. But how do you do it with analysis? And you come up with an analytic argument, and always the analytic argument seemed to tell much more than the probabilistic argument. That's what Louis was telling me once.
In probability, you make estimates. Okay? The estimates are of two kinds. Mm-hmm. If you have a non-negative function, which is large on a set, then the integral is large. And the converse, if the integral of a non-negative function is small on a set, the measure of the set where it's large is small.
Mm-hmm.
These are the only two inequalities that you use for estimating anything in probability theory.
Do you tell this to the students who are coming to work? You only need to know this fact?
The trick is what function do you use to estimate it?
Yes.
In PDE, this is maximum principle. It's nothing else but maximum principle. So any argument that uses probability, if you don't want to use probability, can be translated to an argument that uses maximum principle. So you can make a correspondence between the two. And the PDE method, you have the option of differentiating the equation once and doing other tricks, which allows you to get some estimates and more information.
Which you can't do in probability.
In probability, it's very hard because it's difficult to differentiate a measure which depends on a point. It's a lot easier to differentiate a function with respect to a variable.
Right. Let's go back to the homogenization. There is a very famous work of yours with George and Pierre-Louis Lyons, which is unpublished. The most famous unpublished work, the most cited unpublished work in the history of mathematics as far as I know. So can you tell us a little bit about the problem and the work, and why wasn't it published?
That's difficult to say. I'll tell you my version of it.
Okay.
But George may say have a different version, and Pierre-Louis may have a different version.
I want your version. Let's hear your version.
I think it happened, Pierre-Louis was visiting Courant at some point, and he was interested in homogenization of Hamilton-Jacobi equations. Right. I think periodic case was what he was interested in. I had a way of looking at homogenization which is a little different from how a PDE person would look at it. I'll explain that in a minute later on in a different context. And if you bring that point of view, then the problem can be solved in a reasonable manner. Intuitively you can solve it, find the answer, and to actually prove it, you need to do some estimates. Some PDE estimates are needed to justify your argument. So that's what George and I thought. And we exchanged some emails, and I sent my thing to Pierre-Louis. And Pierre-Louis liked the proof, and then he also thought that would be, the method could be extended much more generally. So he sent back within a week or 10 days a huge document which generalized it to a much higher generality, not periodic but random and so on. And somehow George and I didn't have the heart to sit down and go through it. And it just stayed dormant for a while. And if something is dormant for a while, it's much harder to bring it alive. But it's not true it was not published. I think Pierre-Louis published it in somewhere, a version of it. It maybe not as a paper, but as part of a monograph. Or somewhere it does appear.
Somewhere? Okay.
Somewhere it does. That's what I was told.
I have a handwritten copy that I once got from you.
That is Pierre-Louis' handwriting.
Okay, that's the only one I've seen in my life, so this is why I'm going back to that paper. Okay, but you said something very interesting. You said, I have a different view of looking at the problem. I'll explain it in a minute. So what was your point of view?
See, in general, if you have a homogenization problem, it's a limit theorem. So some averaging has to be done. The averaging is not done with respect to Lebesgue measure, unless the problem is a reversible problem. The problem is not reversible, then one has to be careful about what measure you use to average. And if you have in the end you want to prove an ergodic theorem. The ergodic theorem means that it's a time average that you want to prove. And if you think of it in a moving reference frame, because you're discussing, studying a particle that's moving, in a moving reference frame, then the environment changes as you move. So what you really want to know is what is the invariant measure on the environments as seen from the particle. So that's the calculation you need to make. And if you think of it that way, then things fall into place. And then I was talking with Dan Struck at that time, who was a graduate student just finishing up that year at Rockefeller. And we said, can this relationship be used, in fact, to define diffusion process? See, probabilistically, in order to define a diffusion process, there were two techniques available. You could use PDE, which meant you wrote down the heat equation with those coefficients, you got the fundamental solution, and you use the fundamental solution to define a Markov process, the way Brownian motion is defined.
Right.
So you depended on the PDE for that. Other alternative was to use Ito's theory of stochastic differential equations.
Right.
And then there was a relationship between the paths of this process and Brownian motion, and it's like an ODE perturbed by noise.
Right.
So you solve this noisy ODE, and the input noise gets converted to a diffusion noise in this process. That's another way. And that requires some Lipschitz continuity because it's the ODE stability method on the objects they define. And the ODE, and the object that comes is the square root of the diffusion tensor. So basically your Aij matrix should have a square root that's Lipschitz for the Ito theory to hold.
Right.
But it doesn't require ellipticity. Whereas PDE often requires some ellipticity methods, but in terms of regularity, just Hölder continuity of the coefficients are enough, or even less if you are satisfied with solutions in Sobolev space.
Right.
That was not satisfactory from a probabilist point of view, because from a probabilistic point of view, the object you were interested was a measure in function space, which represents the probabilities of this diffusion process. It's not the paths that are central. It's not the PDE central, it's rather this measure on function space.
I see.
So the measure on function space somehow is constructed from the coefficients that define the diffusion.
Right.
So can you write down a direct relationship between the two that bypasses both Ito and PDE? Well, you can write down saying that certain expressions that are constructed out of the coefficients are martingales with respect to this measure. Turns out that that formulation in some sense is equivalent to the usual formulations under the usual conditions. But the formulation is general enough that it doesn't require any regularity to formulate it. Doesn't care if the spaces are finite dimensional or infinite dimensional. So it's a very general formulation. But of course, in this formulation, you have to prove theorems. So first thing you need to prove, do solutions exist? Turns out existence is much easier to prove. Because existence, basically, if you assume just continuity or something like that on the coefficients, it's like proving existence of solutions for ODEs just under continuity.
Right.
It's the same philosophy. So you can prove existence. But uniqueness is a lot harder. But one advantage in this method is that it sits on the borderline between analysis and probability. So if you want to prove, you could prove results using probability, or you could prove results using analysis in this formulation. For instance, one of the easiest things you can prove is a localization. In fact, you can prove that the uniqueness is a local property. And then you can show that if there is uniqueness in the PDE context, which means the existence of smooth solutions for the heat equation, then there is uniqueness here. Or if Ito's equation has uniqueness, then it has uniqueness here. So if you have a problem where in certain pieces it's smooth but not elliptic, in certain regions it's elliptic but not smooth, this works both places. So it sort of unifies the whole thing. And also various other consequences like Girsana formula and things like that are very easy to prove here. All this is not very hard. It's once you formulate it, it's not that difficult to prove. In fact, we are able to prove these things fairly quickly. But we wanted to prove something more general than what is known. Use this. And we said as our goal, can you prove uniqueness just under continuous coefficients? Assume ellipticity and continuity, but no holder. That means your solutions are only in some Sobolev space.
Right.
That means you have to know a priori that your stochastic process somehow has some LP regularity to otherwise you can't use the duality.
Right.
So you have to get some a priori estimates on the probability that you can work with the Sobolev. And that eluded us for a long time, for almost a year and a half.
That's a very tough problem, I know.
Marquardt has a wonderful source of problems. And one of the problems he posed is what's called Wiener sausage. That's an interesting problem. It has to do with, the idea is that you have a Brownian path that wanders around, and there are traps. These traps are randomly distributed according to Poisson distribution, and each trap has a radius around it, and if you go within the radius, you die.
Right.
So you want to know what's the probability of survival for a long time, T. So you can see that there are two ways you can survive. You can survive by carefully avoiding the traps. You can survive by praying that you don't have any traps. It turns out that in terms of loss deviations, it's the prayer that matters.
Oh.
Okay? What it means is that it's conceivable that you have a large region without traps.
Right.
It may not be where you are, but somewhere out there will be some large region without traps. So you make a beeline there and rest comfortably there. The price you have to pay for resting comfortably in a large region that you found is much smaller compared to the price you have to pay for avoiding traps all the time. Because then you have to be always alert.
Right.
Here you have found a nice place and you can rest free. And to actually prove this intuition requires some large deviation theory, some scaling, and also fair amount of complicated analysis. Because when you do the scaling, the traps become very small. And while it's not that difficult to prove that this strategy is a good strategy, to prove that there is no better strategy is harder. It turns out that one of the interesting comments that Marquardt made, well, if this problem is too difficult for you to solve, then you can do the same thing for random walks. that would already be significant.
Right.
But it turns out that the random walk problem is harder because you have to prove convergence to the by center limit theorem to Brownian motion, and it depends on the Brownian motion result for the answer.
You mentioned a couple of things here that I would like to pick up on: the particle system and hydrodynamic limits. So I will go there with this conversation. So I believe this was what interested you when I came to Courant.
Yeah, in the early 80s, I was at a conference in Lumini. George Papanikolaou was there, and that was an interesting conference because we had a barbecue one evening with excellent seafood from the Mediterranean, and the next day we were all sick. All except Barry Simon.
Oh, well, I'm not surprised.
Anyway, maybe not that day, the day before or the day after. We went down to the seashore and down a hike after lunch, and George explained to me this problem of basically particles interacting through binary interaction and subject to some noise in terms of diffusion. And if you put large number of such particles in some domain and you rescaled it, somehow in the end you should have a flow for the density in the limit, because the only conserved quantity here is the particle number. So the limit, think of it as a conservation law, there should be some sort of a nonlinear, because of the interaction, nonlinear heat equation is what you should get for the density. And one can guess what the diffusion coefficient should be from non-equilibrium statistical mechanics. And the question is, how do you prove it? He had a graduate student, Guo, from China at that time, and they did succeed in proving fluctuation result. Fluctuation means that you are linearizing around a global equilibrium, and so it's considerably simpler than proving convergence in non-equilibrium. So when I heard the problem, I thought, it shouldn't be that difficult, because you just look at it like any other limit theorem. But I found I couldn't, it was hard. It was just not possible to do it at that time. So that stayed unsolved. But the problem was always, I was always thinking about the problem. And as with most problems, you think about it, you make progress. Most of it is in place, except one lemma you can't prove. And if you could only prove that one lemma, the whole thing works.
Right.
But anyway, that was the way with this too. But then I think a couple of years later, we had a visitor from Budapest, Josef Fritz, who gave a talk on a different model, field theoretic model, not a particle model, on the similar hydrodynamic scaling problems. And then I realized that the lemma I couldn't prove, in his case, I could prove.
For his model.
For his model, I could prove. And in fact, we could prove a more general version of his result under much less restrictive conditions. And that's what I did with George and his student. That's what got me interested in hydrodynamic scaling problems.
Right. But that was also a big activity for you and afterwards.
This I think, we did in 85 or something like that. And then for the next few years I had, excellent students. I mean, Fredon, Jeremy Costal, then Pablo Calderon.
Right.
So a lot of students who were interested in this.
And postdocs as well you had.
And then we had many postdocs, Claude Kipnis from Paris, and then Stefano Ola,
Right.
Claudio Landim, and then HTO joined the group. So we had a whole group of people continuing this activity. And so the techniques that we developed at that time were powerful techniques which could handle many problems that was remained unsolved at that time.
Mm-hmm. Yeah, I mean, that work was always astonishing to me. I kept up with that work mainly from the students and the postdocs who were there at that time, and I'm always at awe what you guys were doing as a group. So I'm very fond of it. Again, so let me ask your perspective as a person who was doing the work. Was something, again, that really a result that you like, as you pointed out in the large deviation problem?
One particular result, which is a key to many of the other results that I really liked, was, the model that I worked with George and his student is a model where, the underlying diffusion was a constant.
Mm-hmm.
So I said, what happens if I replace that constant by a function? Not a constant, but nice elliptic smooth function.
Right.
Then the level of difficulty of the problem increases by an order of magnitude.
Mm-hmm. Mm-hmm.
I never really could understand why. At some point you do integration by parts or summation by parts,
Right.
and that eats up 1 power of n.
Mm-hmm. Mm-hmm.
If it's variable coefficients, you can't do it.
Right.
So you don't know what to do with that big n staring at your face.
Mm-hmm.
But then I found some way of doing it, using some large deviation to solve that problem. What it really involves is doing some kind of a cohomology type thing in infinite dimensions. There are certain functions which are certain types of gradients,
Mm-hmm.
and then there are certain other class of functions, and you want to show that the codimension is exactly what it should be. And if you take a representative with the orthogonal complement, that gives you the way of computing the diffusion coefficient. So it's a complicated piece of work. But somehow I arrived at it, and that's what Jeremy used to prove his results on particle systems and so on. But I still didn't understand why it had to be like that. Because that was mainly because my knowledge of statistical mechanics was very weak. Then I was at a conference and I told someone what I could do, and they explained to me that there are gradient and non-gradient models. And the so-called Green-Kubo diffusion is easy to compute in gradient models. But in non-gradient models, it's really impossible to compute, especially in non-equilibrium non-gradient models. Nobody has really computed it, and it's thought to be very difficult. And what I had done was really a method for approaching that problem.
I see.
So once I found out that's what it was, then we could do many other.
Right, and then you appreciate the difficulty as well. You are still very active in probability, but since you started working in probability and now the field has developed enormously and it touches more and more areas. I go to colloquia at Courant and I hear how probability is playing more roles in computer science and other branches, and new type of ideas are developing. So give me some of your feeling about the subject and which way is it going? How is it developing now?
There are many changes that are taking place in probability. I think when I was growing up, in the sense that when I was 20, 30 years ago, when I was developing my interest in mathematics, the probability was more closely tied with analysis. The active areas of interest were diffusions and properties of diffusions, which is very much PDE. So my intuition in that sense developed in that context. So I'm comfortable with thinking about diffusions. I have a feeling for what they can do, and I can interpret my intuition in terms of properties of solutions of PDE, what you need to prove for PDEs in order to justify this intuition. I can go back and forth, and that's what I exploited to a large extent. But now the subject is no longer that much related to PDE, although PDE still enters, but the connection is much more on the combinatorial side. I think most of the work connected with percolation and things like that that's going on now is connections with certain combinatorial aspects of probability. And there are interesting limits which some differential equations show up, but these are very specialized equations for a specific context. I do not have the necessary intuition which I have not developed for these things. So I have not been that active in these areas. But still there are problems there which have something to do with large deviations. There are some natural large deviation questions that come up in these areas. And I'm, of course, very much interested and try to follow what goes on as much as I can.
Right. And this is the type of probability that's finding its way in computer science, combinatorial kind of.
Yeah, there's a lot of connections between them. If you look at many of the talks and so on, they all have this flavor nowadays.
But the field is quite healthy. It's developing.
The field is very healthy. I think the health of a field depends on opening up new areas and attracting new talent. I think nowadays, if you take our incoming graduate students, at least half of them want to be in probability.
Right. At least at Courant, they want to. That's absolutely true. Absolutely true.
Maybe they want to go work on Wall Street afterwards. Maybe, but still.
I remember once you told me how in the beginning the probability was not respectable. So maybe you want to tell us a little bit about the beginnings of probability.
At least that story I hear. Probability developed in France. Statistics developed in England.
Right.
The Brits would have nothing to do with probability because it's related to gambling. And for Protestant ethic, it's a sin to gamble. So the British could not conceive of doing probability.
So we came a long way from that.
A long way from that. One of the things that I always try to do is, if you have a problem, first you have to develop some intuition for the problem. The intuition says something happens, and then you want to show that this is true in a rigorous mathematical sense. The ideal thing would be to sort of analyze your intuition and see if you can translate your intuition, somehow legitimize it into rigorous language. Otherwise, having an intuition in one way and then verifying it by some long computation is not really satisfactory. I think somehow you have to convince yourself that your intuition was correct and based on, in fact, reasonable logic.
So after this very long chat, you've done probability now for over 40 years or so from your studies, 50 years. So where do you see where we are at now in its development and the way the subject is moving?
I think the subject is in a very exciting phase right now. New developments, Of course, it's always changing.
You spent all your career at Courant.
That's right.
As from the very beginning. So one thing that I'm curious about as an immigrant as well is that did you intend to stay in the US when you left India?
No, my idea was to stay here for 3 years and then go back.
Yeah, 3 years seems to be standards for immigrants who stay here a lifetime.
For a reason that when you want to come here, you came on a J visa.
Yes.
And the J visa was granted for 3 years, and then the visa
Right.
was not renewed. So
You don't want to go through the hassle of renewing the visa or trying to renew
no,
it.
I think they renew it twice, and then they
Right.
won't anymore. You have to go back to your country for a couple of years to come back.
The institute must, when you came till now, it has changed enormously. You were director on a couple of occasions. You became director of the institute. The institute has grown enormously from the time you came until now. So in the beginning, and how the atmosphere changed from the beginning till now, maybe we can talk a little bit about that.
See, in the beginning when I came, the institute had sort of 3 groups. There was the Heights group, run by Joe Keller.
Right.
There was the Washington Square undergraduate group, run by Morris Klein.
Right.
And then the Courant Institute graduate group, run by Stoker at that time. Okay. So the faculty were different. They were entirely different faculty. They were appointed to one or the other. And that created some friction, because people felt that they should be the institute faculty. If you're in the institute faculty, you only teach graduate school, you don't teach undergraduates. If you're in the undergraduate faculty, you don't teach graduate courses, you only teach undergraduate courses. And that created, some friction. And fortunately, all that went away over time. Of course, the Heights just went away.
So when the Heights disappeared, all the people moved to
Many were
Washington
let go.
Square?
Many non-tenured faculty were let go.
Right. But the tenure faculty, you absorb them on the square. It's one department.
The tenured faculty came down.
Came down. And so what did that do for your space? Was it tight?
No, we had a lot of space, because remember that at that time we didn't have a computer science department.
That's true.
And we had a lot of room for visiting members and so on. So those days visiting members had their own private offices. Now they have 2 to a room, or sometimes even 3 in a room. The space was not a problem at that time.
Now you came to the institute, and as you said, it was in the hat factory and part of it in Fort Washington Place before moving to the current building and on 251 Mercer. And Richard Courant was still alive.
Oh yeah.
Did you get a chance to meet him?
I met him socially at dinner at Donsker's place a couple of times. And he comes to tea if he's in the institute, just to say hello. And, I don't think we had any serious conversation for any length of time.
But how about Friedrichs and
Friedrichs and Fritz had
Stoker?
Stoker, after retirement, was always interested in what was going on at the institute. So when I was director, for example, we would meet periodically for lunch or something like that. He would ask me how the institute was going and so on.
What was the size of the institute at that time?
I think the faculty was probably 20 to 25. This is the graduate faculty when it started. With the undergraduate faculty combined was in the 30s, 35. That was the size of the faculty.
When I came, you were a director, but that was the end of your directorship. When did you
I
start?
think 80 to 84.
Okay, so I came in 83, you were a director for a year, and afterwards you took another directorship in the 90s.
Yeah, that was not planned.
Between these two periods, there was also a big change in the size of the institute in terms of faculty.
NYU started building up.
Mm-hmm.
They wanted to strengthen their science departments, and they went through a program of expansion.
Right.
Part of the expansion was increasing the size of the student body. When you want to increase the size of the student body, instead of 2 or 3 sections of calculus, now you are giving 20 sections of calculus, right?
Mm-hmm. You have to have faculty.
So you need more faculty.
Right. One thing that's very well known when I came to the institute were the lounge and the lunches at the lounge, and it became part of my daily routine as to go up and have lunch with all the faculty. So it was like that before the building was built, because you had no lounge before.
We had tea rooms in both places. There's a tea room in 4 Washington Place and the tea room in 25 Waverly Place.
Mm-hmm.
We used to go there for tea.
Okay.
Cake and coffee were 5 cents each.
Those were the days. 5 cents for a coffee. Now it's $2 anywhere in Manhattan.
Lunch, we always went out as a group. There are a lot of restaurants. And before, the doctors discovered cholesterol.
Yeah. Now, the lounge played an important role and still plays an important role for many of us. And I know you are one of the regulars who come out for lunch. So there must have been many interesting mathematical problems that started in the lounge through a discussion.
I think they still do. And I think one thing that's I find different now, I don't see the reason for it, is in the old days, the graduate students were there too. We often sat at the same table with graduate students, right, and talked freely with them, and not necessarily about mathematics, about politics, and so on. So that built much closer relationship with graduate students. Now I hardly ever see graduate students at lunch table.
I'm curious to see if there is one of these famous results that started as a question over lunch. Like, so did somebody pose a question for you? I know that.
Sure. I mean, just a year ago, for example, we have a new faculty member, Saurav Chatterjee. Mm-hmm. He asked me a question on graphs, random graphs. Mm-hmm. So I thought about it, and it was a large deviation question. I knew what the answer should be, and in order to prove the answer, I needed a lemma.
As usual, we all need a lemma.
So I was at the lounge, and then Joel Spencer was there. I told him what the problem was, and I needed a lemma for this. He said, yes, the lemma exists. And he gave me a reference for the lemma. And it was called Shamaredi's lemma.
Oh, that's a famous lemma.
Famous lemma in combinatorics. So I just didn't know, so that was just what I needed to complete that work with Saurav.
Right. The other thing that I found it to be very charming when I came, and I'm very curious how it was before I came, is the Christmas party in the Institute. In the old days, when I came, it was still all the people from New Rochelle came down. Louis used to come with a tape to dance at the end of the party.
In fact, the reason the lounge has wooden floors is because Stoker insisted the lounge be available for dance parties. So we had lovely wooden floors.
Yes. I must say, it's very charming to see all the old people at that time dancing waltz in the Christmas party by the end of the evening. It was very lovely.
The Institute has been a marvelous place for me. and I'm sure it's still a marvelous place for all the new people who come in. And it's a unique place in the sense that there is more an atmosphere of family, and people take care of each other and enjoy each other's successes and so on. So I think it's a marvelous place, and I hope that continues.
Hope so.
Among all the foreign graduates, the highest percentage of graduates in computer science, mathematics, physics, and so on are Indians.
Right.
And I think the Chinese come next and the Europe comes third. Particularly in math, computer science, and statistics,
Right.
India is way above.
Well, surprisingly, I find many Chinese students, their interest has shifted from math into financial math. And I don't know if this is an indication that the Chinese population is more interested in the economic growth, like they do business and they do finance, whereas it's always been in computer science that the Indian population among the students is very high since I came to
Yeah, because the IITs, which train excellent students. I mean, the top talent, top graduating talent from high school ends up at IITs.
I mean, in Europe, they have good universities, so I would not be surprised that we don't have a big number in European. In India, they have very
India,
good
there are no
universities.
universities. Absolutely no universities.
No, but your undergraduates are excellent. You don't have graduate schools, you mean?
What undergraduates? Outside of IIT, where do you get undergraduates from?
Yeah, but how many students do you have in IIT? I mean, all around the institutes in the country, not only in...
Most of the graduate students you have here who are good are from IITs.
Right.
Most of the major universities in India don't teach undergraduates. They have affiliated colleges that do the teaching. The university only grants degrees based on an exam. The universities where I went and got my honors degree, that program doesn't exist anymore.
Why doesn't it exist? What happened?
Education is a state responsibility in India.
Yes.
So the universities are run by state governments.
Yes.
The state governments are very parochial. They will not appoint to the faculty if you are from a different state. Say, I am from Madras, Tamil Nadu.
Right.
Bombay University will not appoint me
On their faculty.
on their faculty because they will say, well, we are Marathi speaking people, you have to be able to lecture in Marathi.
Even though everyone lectures in English, most
That
likely.
may be, but that's the excuse they use.
Mm-hmm.
And state administrations are very corrupt. In Tamil Nadu, for example, there is discrimination against the Brahmin community.
Mm-hmm.
And the Brahmin community is what produces traditionally scholars and scientists and teachers,
Mm-hmm.
and they will not be hired, even if you're from the same state. So the Ramanujam Institute, which is run by Madras University, is a scandal. Half the jobs have been vacant for 20 years. They are not appointed. They're running it to the ground.
That's really difficult to believe because there are so many qualified mathematicians.
They all come from institutions, right? Tata Institute is an excellent institution which trains excellent graduate students.
Okay.
Okay, but they take in 3 or 4 a year.
Is that it?
That's it. You count in your hands how many people have come out of Tata Institute. Good people have come out.
No, I did not know that the numbers is so small. I imagine there's the Tata Institute.
The demand for PhDs in the committee in the country for training next generation of students and so on is enormous. They could appoint 500 PhDs in mathematics to faculty position for the next 10 years.
Yeah.
I will say, I'm a little harsh, the country perhaps produces 5 to 10 good PhDs in mathematics every year. Most of the universities, what happens is the faculty is a professor who was appointed some years ago, does something, nothing very original, something he's been doing for 30, 40 years, little extension there, nothing at the cutting edge. He is a graduate student, he gives him some problem, he solves it, he gets a degree, he's appointed at the same university to continue the same thing.
I'm not surprised by that, because once I was on a committee for evaluating universities in Portugal, and I found smaller universities do exactly what you just said, but on a national level to be happening in almost all universities is scandalous. I mean,
the government is not unaware of this. The central government is aware of this, and the establishment is trying to do something about it. Okay? But politics being what it is, central government no longer has an absolute majority. They had the coalition government. The coalition government is a combination of local parties in states. And the local parties in states govern their own state. And so the central government cannot force things on the local government.
India produces many doctors, for instance. Why is it they're producing doctors and not able to produce other kind of professionals?
The top talent, goes to engineering, IITs, and to the medical schools. That's what attracts the best students. The central government runs its own set of medical schools, and they have a competitive exam that you take in order to enter. And the states have medical schools which are reasonably well run.
And they produce money more than mathematicians.
So IITs do not teach basic science. They have math departments, and there are a few good people in math departments. But remember that India is a country of 1 billion.
Yes.
Okay? And the university population is enormous. Okay? So there are umpteen million colleges. If you count how many are good all-round universities that offer undergraduate education at internationally recognized level, there aren't any. The central government has opened, just within the last 4 years, a half a dozen ICERs, they're called. It's like IITs, but for basic sciences. The central government is throwing money and starting new institutions. But still, that's still a small number for the country of its size. They won't produce PhDs for a long, long time.
True, but I mean, it's a step similar to what the Chinese have done with many universities that they have established as being.
But Chinese undergraduate education has always been good.
Yeah, but the number compared to their population, I mean, right? We can name a dozen Chinese universities which have been good.
I can't name 2 in India. It's sad in a way, because when I was growing up, the university education system was good. We once had it. Because people are aware of the problem. I think the government is aware of the problem and is trying to do it. But I think in order to actually achieve any success, they have to attack the problem in several fronts. And just starting a small number of elite institutions is not sufficient. You need to produce a large number of good undergraduates in basic science so they can then go on, and you need a large pool out of which excellent people can come up.
But I mean, this must be happening as well, because India is finding new wealth. I mean, if you'll compare the state of India economically back, say, 20 years ago versus now, there's no comparison. Now it's doing much, much better, right?
Economically, it's doing very well.
So some of the money must be going, the central government must be putting money in.
Money is not the issue. The government has enormous resources and is willing to put it in education. But you can't just throw money and get education.
No, but you need money to attract people, to build universities. So,
but the problem is lack of faculty. Right? It's getting better now because you're able to at least attract the faculty back from the United States because they find better opportunities in India.
right.
But that may change at any time.
In the US in the 50s, there were very little research institutions. And then with the space race with Sputnik and the promise of Kennedy of putting some man on the moon within 10 years, that came, with it came lots of funding and increase of research universities, and therefore we were able to have an enormous supplies of scientists and engineers and people working in basic science.
Also during this period, there are many political refugees from Europe who came here, who were very well qualified scientists at the height of their research career, who came and who were enormous help in building up the research ambience in the United States.
Sure, they built the Courant Institute.
I believe it was about Hans Rademacher. I heard this story. He came for a job interview at some small college, and he came, and the chairman of the mathematics department interviewed him, and they had some pictures of famous mathematicians on the wall, and he saw his own picture there. So he interviewed. He said, "That's me." So the chairman said, "Okay, we'll decide going to come next week." He came next week. He didn't get the job, but the picture was gone too.
I think I heard it about Hadamard, so it must be one of them.
China has, because it's a centralized system, has strict standards. At least all the major universities are very well controlled and very well run. And the large universities train undergraduates.
That's absolutely true. And they don't have the state system. I mean, in China, you take a national exam and the talent is sent to the best universities around. It doesn't matter if you are from Yunnan province, you might end up in Beijing, irrespective of your ethnic or local, whatever you belong to, the province.
And China, has always had a large number of active mathematicians doing research, working at the universities.
True, but I mean, again, the numbers are not that great, I think. There was not that great in this.
Yeah, the Cultural Revolution, of course, got rid of most of them.
Right.